In the previous example, we were able to put our system into state space form sort of by blind mathematical manipulation, by a simple change of variables. It turns out that there are better ways to choose our set of state variables, i.e. better ways to put our system into state space form. Specifically, if we blindly do this change of variables, we may end up with a situation where we're using more state variables than are necessary. We're using a larger set of equations than we need to. If these set of equations are not linearly independent, then it can make it difficult or impossible for us to solve the equations and to design our controller based on this model. And so it turns out that there's a sort of more intuitive way to choose our set of state variables that will guarantee that we use the minimum number of state variables. In order to understand this approach, we need to recall the difference between a static model and a dynamic model. So consider our system. We understand it in terms of inputs that we put into the system and the resulting outputs that we get out of the system. If our system is static or our model is static, knowledge of the current input completely determines the current output. So if I know that a 5 is being put into the system, then that completely determines what the output of the system is. Along with that, as soon as the input is changed to 5, the output instantaneously changes, and that relationship is basically algebraic. Most physical systems don't behave that way. You know, if our system is a motor and I apply 5 volts to the motor, that doesn't tell me what the speed of the motor is necessarily. Specifically, you know, the motor will behave differently if right before I applied the 5 volts I was applying 0 volts, or right before I applied the 5 volts I was applying 100 volts. That past sort of affects the current behavior of the system. And when I change the input to 5 volts, the output doesn't change instantaneously. It takes time to react. There's inertia. And so with a dynamic system, we can sort of define its state. And the state of the system basically captures that history. It captures all of those past inputs. And so the question is, what initial conditions do I need to capture the system state? What set of variables will capture all of the history that came before this instant? And so with that in mind, we're going to define some terms. We're going to define the state of a dynamic system as being captured by a set of variables. And if we know the values of these variables, then we know the state of the system. And if we know the state of the system at a current instant of time, then knowledge of future inputs will completely allow us to determine the behavior of the system. So, you know, the sort of capturing of the state captures everything that happened in the past, and therefore knowledge of the inputs allow us to predict what's going to happen in the future. And it turns out, and it will be somewhat intuitive, I think, that the minimum number of state variables that we need, the minimum number of variables to capture a system state, is equal to the number of independent energy storage elements. So the energy stored in the system at a current instant of time affects the behavior of the system going forward. And so if we can sort of capture or determine the energy that's stored, then we can determine what's going to happen in the future. So let's consider this example. It's a little mass spring damper example. These are the equations of motion. We know how to derive those equations of motion. We could do it by drawing the free body diagrams for each of those two masses, using Newton's second law to write the equation of motion for each of the two masses, and this is what we arrive at. And so by inspection, we can see that this system of equations is not in state space form. You know, each of the equations is a second order differential equation. So we have a second derivative of y, its first derivative and the function of itself. The function itself, same thing with the second equation. So one way to transform these set of equations into state space form is just to do a blind substitution. And so this is what we had done previously, but we had two second order differential equations, and we can transform them into four first order differential equations just by using this change of variables. It turns out that this set of state variables is not minimum. It turns out that we can put our system into state space form with a smaller number of state variables than the ones given here. And the way that we'll do that is by trying to identify where energy is stored in the system. So specifically, we'll find elements within our system where energy is stored, and then we'll determine an associated variable that allows us to calculate how much energy is stored in that particular element. So take a second, look at this system that we have from previously, and think about where energy might be stored. And so the first thing you might identify might be the spring. And in particular, a spring stores potential energy. So you can imagine that if this spring is compressed and you let it go, it'll push the two masses apart. If the spring is stretched and you let it go, it'll pull the two masses together. And so right there, you sort of get a sense of what a dynamic system is. You get a sense of how that spring being stretched or compressed would affect the motion of these two masses. And so what we need is we need a variable that captures how much energy is stored in that spring. And specifically, the amount of energy stored in the spring is determined by its amount of deformation. And so in this case, if we assume that y and z are 0 when the spring is at rest or undeformed, then the deformation of the spring will be determined by the difference in the motion of this end of the spring and the motion of that end of the spring. So the difference between y and z. So this is our first state variable. It captures how much energy is stored in the spring. In addition to potential energy, there is also kinetic energy stored in this system. And if you recall, kinetic energy is 1/2 mv squared. So each of those masses stores as kinetic energy. If we consider mass 1, the energy stored in it is determined by its velocity. And so since its position is defined by y, its velocity is y dot, and that defines how much kinetic energy it has. And so again, just like the spring being compressed or stretched will affect the behavior of the system going forward, if this block is initially moving or is initially at rest, that will also affect the behavior of the system going forward. You know, it's just like with our motor. Was a second ago was the motor at rest and we were applying 0 volts, or was a second ago we were applying 100 volts and the motor was going very, very fast. Analogously, mass 2 also stores kinetic energy, where its state variable is its velocity z dot. And so right away we can see that these three state variables capture the state of the system. You may have a question about, well, what about the dashpot? Well, it turns out that dampers don't store energy, they dissipate energy. You can sort of imagine if these two ends of the dashpot are being moved relative to one another, you're sort of pulling this plunger through this oil and it's sort of generating drag or friction, and that oil's heating up. And so that's where that energy is going. It's being dissipated in the oil or in friction or in air drag or whatever. And it's lost as heat, and it's not readily recoverable. Okay, so that energy that you're losing in the form of heat, you can't get back. So here we sort of show how we can find the minimum number of state variables for a system in sort of an intuitive way. And we sort of get a sense of this notion of a dynamic system state. Something that's interesting to point out is that the choice of state variables is not unique. For example, previously we had chosen our state variables to be y, z, y dot, and z dot. So if we knew y and z separately, we have just as much information as when we have the difference between y and z. So if I know y and z separately, I can also determine the amount of energy stored in the spring. And so that set of 4 also captured the state of the system. It just turns out that it's more than was necessary. We don't actually need to know y and z individually. It's enough to know their difference. So here again is our system of governing equations. Here's the set of state variables that we've generated by determining where energy is stored in the system. And let's go ahead and rewrite these equations in state space form. So we start by writing a differential equation for each of the state variables. Okay, so x1 dot is simply y dot minus z dot, where y dot is x2 and z dot is x3. So that's our first state equation. x2 dot is then y double dot. Y double dot is not any of our state variables directly, but if we look at this equation up here, we can rewrite y double dot in terms of these other variables. So x2 dot is y double dot. If I solve this equation for y double dot, I can divide through by m1. I can subtract this term over to the other side, where y dot is x2 and z dot is x3. Then I can subtract this term to the other side, where y minus z is our state variable x1. Okay, and similarly we can do the same thing for x3 dot, where x3 dot is z double dot. And using the second governing equation, we can rewrite this in terms of our state variables. I can isolate z double dot by dividing through by m2. I can subtract these terms to the other side. So minus b times z dot, where z dot is x3, minus y dot, which is x2, subtract k times z minus y, where this is negative x1. So a negative x1 and the negative will become a positive. And I already had the u on the right-hand side, and it's left there. So here I've rewritten these two governing equations, second-order differential equations, as a series of 3 first-order differential equations. Since they're linear equations, I can put them into matrix form. So I'll define my vector of the derivatives of the state variables. It's going to be equal to my A matrix multiplying my vector of state variables x1, x2, and x3, plus my B matrix multiplying my inputs. In this case, I just have a single input u. So the first row of this equation represents my first state equation. So I have nothing multiplying x1, I have 1 multiplying x2, and negative 1 multiplying x3, nothing multiplying u. The second row will be the second equation. If I distribute this, I'll have a coefficient of negative k over m1 for x1. I'll have a coefficient of negative b over m1 for x2. And then the negative multiplying the negative becomes positive, so the coefficient for x3 will be positive b over m1. There is no u term, so the coefficient for u is 0. And then the last row of my A matrix and my B matrix will come from the last state equation. The coefficient for x1 will be k divided by m2. The coefficient for x2, a negative and a negative will become positive, so I'll have positive b divided by m2, and then the coefficient for x3 will be negative b over m2. So that completes my A matrix. For the B matrix, I have a coefficient for my input u as just 1 over m2. And so that defines my B matrix. So this matrix equation captures our state equations. We also will have output equations where the output is either told to you or determined by engineering judgment. So let's say that the output is hypothetically so we'll say that y dot is equal to the output. Just to avoid confusion, we often call y the output, but since we already have a variable y, I'll just go ahead and say w is the output. So it'll be a C matrix multiplying my vector of state variables, and then a D matrix multiplying my input, which in this case is just u. So if y dot is the output, y dot is x2. So I'll have 0 times x1, 1 times x2, and 0 times x3. And there's no u in our output. So this defines our C matrix, and that defines our D matrix. And that completes the transformation of this system into state space form. A couple of things to point out in terms of when the minimum number of state variables doesn't equal the number of energy storage elements. Previously, we had sort of made the distinction that the state variables is determined by the number of independent energy storage elements. So for example, this spring is an energy storage element, but if I had a second spring, I have 2 energy storage elements here, but the energy stored in each of them is both determined by the same state variable. So I don't need a separate state variable for each spring. I can use the same one because they're dependent on one another. Same thing with these 2 masses. If m3 doesn't slide relative to m2, they will have the same velocity. I can use the same state variable. If I have this disk here, if it's rolling without slip, then the motion of m1 is geometrically related to the motion of the disk. I don't need another variable to capture the speed of that disk, and so on. So if some elements are constrained together, i.e. if they're dependent on one another, then they don't need their own energy storage element. Another situation where we might need extra state variables if some terms in our equations can't be expressed in terms of the minimum number of state variables. So in the previous example, x1 was equal to y minus z. If it turned out that we wanted y to be our output, then we would have to break this up. We wouldn't be able to express the output in terms of x1 and x2 and x3 if we wanted to control y, or we wanted to know what y was doing. So that would be a situation where we would need extra variables in order to get the output that we desire.